All right, so let's go ahead and start section 15.7. You know, last year, after you learned about derivatives and everything, you learned also how to find maximum and minimum values. So that's what we're going to do. There was your first derivative test and your second derivative test, so we have things similar in 3D. But anyway, just like in single variable calculus and 2D graphs, you have different types of maximum and minimum points, right? You have your local max, you have your local mins, and so those were just things. An absolute maximum can be a local max also. So you know, your high points are your maximums, your low points are your minimums, but then you also had absolute maxes and absolute minimums, right? So you had those four things, and so your locals were like a high and low in a region. Right, and these were the high and low, like on the whole graph. Right, so that's what those words were. All right, so like this might be the highest point in that area, but it's not the highest point on the whole graph because it's that one right there. Okay, so when you did this, you used things like your first derivative test, right? And remember, like you would be testing like certain places, and you'd have, you know, a plus, a minus, and a plus, and you're like, oh, I was increasing, then decreasing, so this must have been a maximum. I was decreasing, then increasing, so this must have been a minimum. So things like that. And your second derivative test, you did a similar thing here, but you were testing concavity, right? So your second derivative was greater than 0, that meant concave up, and etc. You know, like, and less than 0, concave down. So also remember your critical points. Oh my gosh, critical points were when your derivative equaled 0 or when your derivative did not exist. All right, so those are how you found your critical points to like put in your test right here, right? Or to put in the second derivative test, which could look like this too. Okay, so we have similar things in 3D, but here we go. So we're going to use some of the ideas now, but so there's a theorem that says if a function has a local maximum or minimum at a point, and the first order partial derivatives exist there, then your first order partial derivatives have to be equal to 0. Okay, so that's going to be an important thing, that our derivatives equal to 0, just like we did up here. And then a point A or B, or sorry, A comma B is called a critical point, or it's also called a stationary point, if your first order partial derivatives are equal to 0, or if one or the other of these partial derivatives does not exist. So usually we're going to be using this situation here, but the other one is also true. Okay, so let's find some critical points here. So you can see that, you know, there's this picture right here, so you do have to kind of like know some of your shapes again, but anyway, it's a paraboloid right here, so we're going to basically end up finding this point right here. So let's go ahead and do, I forgot an f right here, let's do our fx and our fy. All right, so my fx would be negative 2x, that's gone, plus 2. That's gone and that's gone, right? My fy would be negative 2y plus 6, and the rest is gone. So remember, what has to happen is that these two things have to equal 0, all right? So this is like a system of equations, like they both have to equal 0 at the same time. So these are fairly simple ones. So if I solve this, I set it equal to 0, I get 1, so x has to be 1. And when I set this equal to 0 and move the 6 over and solve it, I get y equals 3. Okay, so I need both of these to be true. So it turns into a system of equations. Okay, so later we'll have like, excuse me, harder problems. But anyway, so x is 1, y is 3. So that's a critical point. All right, 1, 3, and let's find the z value. So plugging 1 and 3 into here, I get negative 1 minus 9 plus 2 plus, let's see, 18 minus 8, so what's that, 10 and 2, that's 12, so 12 minus 10 is 2, so that's 2. All right, so look, if you actually graph this, that's this point right here. 1, 3, 2. Now, this is just, we were just finding the critical point, but based on what we can see on our graph, that is a maximum point. So there is a way to prove that it's a maximum or a minimum if it is one. But for right now, we were just finding a critical point. So you can see how that found for me this maximum point right here. Okay. All right, so let's move on. So this guy right here. So find the extreme values of this. So we have a saddle, right? So let's go ahead and do this guy. So we need fx and fy. So fx would be negative 2x, fy would be 2y. These have to equal 0 at the same time. So to get this to be true, x would have to be 0 and y would have to be 0. Okay, so you can tell that's the point 0, 0, and this guy right here, if I plug zeros into here, I get 0. So obviously it's like the point right in the center, the origin, right? But this is a critical point, but let's try and tell what it is. So let's look at some of our traces here. Let's so when x equals 0. So when x equals 0 up here, I get the equation z equals y squared. So if I draw this, put my z and my y, I draw it, z equals y squared. So then the point 0, 0 is a minimum. Right? But when I let y equals 0, I get z equals negative x squared. So if I draw with x and y, I get this graph. So then this place is a maximum. So it's both. So if looking at it this way, it's a minimum. If I'm over here underneath, looking at it like from under here, it's a maximum. And so basically 0, 0, 0 is a max or a min depending on your viewpoint. Depending on where you look at it from. So that actually, so therefore 0, 0, 0 is called a saddle point. Right, so that was just a way for us to, saddle points are things that they are maximums and minimums at the same time. So they're called saddle points. Okay. So we need a test. We don't want to have to go through this every time. So we need a test to basically be able to tell us if we have a max or a min. Okay, so here we go. So it won't be too hard, but this next part, let's just take a look, a lot of words here. So once we find our critical numbers, we're going to use what's called the second derivative test to tell if they are maximums or minimums. So this will definitively tell us what we're dealing with. To do our second derivative test, we have to use something called the Hessian matrix. So the Hessian matrix is a square matrix, meaning it's has the same number of rows and columns. So this one has 2 rows and 2 columns, so it's a 2 by 2 matrix of second order partial derivatives. So that means I have my second derivatives right here, xx, yy, xy, yx. All right, so we'll find those and it won't be hard. All right, and notice it's the determinant of those things. So once we get our pieces in here, we're going to crisscross. We're going to do this part multiplied minus that part multiplied. Okay? It describes the local curvature of a function of many variables. The Hessian matrix was developed in the 19th century by the German mathematician Ludwig Otto Hess, or Hesch, I don't know how you say it, anyway, and later named after him. Okay, so here's our second derivative test. So we're going to go ahead and find our critical points by letting our derivatives equal to 0, our first derivatives equal to 0, and then we're going to do the second derivatives and we're going to do this Hessian matrix, then we're going to test those points into our Hessian matrix answer. So remember, we're going to crisscross, so we're going to do fxx times fyy minus these two multiplied, fxy times fyx. Okay, and this will just get us a value or an expression. And remember that these two guys are usually the same. When you have a continuous function, these two are the same. So we don't have to figure them both out. We can at the beginning, but you're going to notice that they're the same. Okay. All right. So here's what we're going to have. depending on the determinant, so depending on this answer, these rules apply. If your d value at the point that you're talking about is greater than 0. So if you're trying the point like, 0, 0, and you plug that in to this answer right here, if you get a value that's greater than 0 and your second derivative at that point is less than 0, then what you have is a local max. So to remember this, I think to myself, I think, the derivatives are less than 0. So basically what we have here is concave down, right? Because if your second derivative is less than 0, negative, then you were concave down, right? So that's why I would have a maximum. Also, you can think of it like the numbers are falling away from it, okay? If your Hessian matrix produces, when A and B are plugged in, something greater than 0, and this fxx, now we could use fyy, but we'll just use fxx all the time, is greater than 0, then you have a local min, right? Because greater than 0, second derivative, means you are concave up, okay? So you have a local minimum. Now if your Hessian matrix produces a d value that is less than 0, then you have a saddle point. And the last situation, if your Hessian matrix produces something that is actually equal to 0, then it's inconclusive. And we are sad because we have to find something else. So the reason that this guy has a saddle point here is because you have mixed behavior. So that's pretty much like this was happening up here, right? Because looking at it one way was a max, another way was a minimum, so like who's to say one is more important than the other? We can't have both, okay? All right, so let's get through like one example here and then we'll stop. All right, let's see. So we know that it's a picture I can see, like look right there, there is like a minimum right there, so let's see what happens. So I need my fx and my fy. So my fx is 4x to the third minus 2, and my fy is 4y to the third minus 1. I'm going to need fxx eventually and fyy. I'm also going to need fxy and fyx. So a lot of derivatives. So xx would be 12x squared, and fyy would be 12y squared. So fxy, so look at this. This has no y's in it. So the derivative fxy is going to be 0. This has no x's in it, so fyx would be 0. See how they match? So eventually, I'm just not going to find this one. I'm just going to do one or the other. Okay. All right. So remember, these two are a system of equations. These have to equal 0 at the same time. Well, they both only involve x's or y's. So 4x to the third minus 2 has to equal 0. And 4y to the third minus 1 has to equal 0. Okay, so basically I get x to the third equals 1/2. So x is whatever the cube root of 1/2 is. And over here I get y to the third equals 1/4. So y is whatever the cube root of 1/4 is. All right, so we'll just leave them like that. Okay, so let's take a look. Let's do our Hessian matrix. My D, so I make a determinant. I put xx here, so I put 12x squared. I put yy across from it, so 12y squared. And then I put these two over here, but they're supposed to be the same, so 0, 0. So let's do this. I crisscross, I multiply these two things, so I get 144 x squared y squared minus nothing. So that's just 144 x squared y squared. Now, this is kind of a special one. Whatever you plug in here, it doesn't matter. This is always going to be positive. So that won't always happen. But anyway, that's always positive. So look back at our list. So always positive, that's great. That means we're going to have a max and min at the point, or max or min at the point that we're doing. So let's check it out. So to check it out, what we have to do is look at fxx or fyy. So fxx at this point that we found right here, cube root of 1/2, comma, cube root of 1/4, what would that be? And I don't really care what it is, I just need to know, is it positive or negative? So if I were to plug the cube root of these, oh sorry, oh yeah, they're both cube roots, sorry, of these two things into fxx, it's going to square everything, so it turns positive, so it's positive. So that means, since my fxx was positive, that means I had a concave up situation. So that means that it's a minimum. Okay. So that means that the coordinate cube root of 1/2, comma, cube root of 1/4 is a minimum. Minimum, sorry. When you talk and write at the same time, it's hard to spell. All right, so is a minimum, and actually from the picture, so that's this point right down here, I can actually further say that it's an absolute minimum. Okay, just based on the picture and everything else we know. Okay, so that's a little bit how to use that, and we'll keep going with that in class, but you learned the first part. See you later. Bye-bye.